Well, I keep getting questions about the 4-wire incremental encoder on this harmonic drive. So we'll take a look at it. I've got a FHAC motor here, and it does not have a 14-wire incremental encoder with Halls and incremental A naught B, B naught X, X naught, and UVW Halls with +5 and ground. It has a 4-wire incremental encoder, and it's just serial data. And it also contains Hall information. So you got +5 and ground, serial data plus, serial data minus, and a shield. So just connect it like normal. Here's a picture of the Copley encoder guide with an incremental A encoder. Now this is not an incremental A like standard incremental A. This would be a harmonic drive proprietary serial incremental with Halls. So you got to use their drive, it's the REL, and you got to use their motor and their encoder and their software. But we'll show you how to hook it up. So you got +5 and ground, serial plus to S, serial minus data to hat S. You know, you got a shield, make sure the shield is connected to the frame on the Copley drive. And if we look at the harmonic drive REL, you can see right on their webpage, they show you which motors it goes to. Okay, the volts and amps, but you can also see the encoder option here. It's 4-wire, so red, yellow, blue, and they show you what pins it's on their connector, and then they show you, how to wire this up to the Copley. So you have to try to view this in a larger detail here. So here's the, I guess, absolute S, yellow, blue, white, black, red, goes to S and S naught, frame ground, pin 1, +5 and ground. And then the motor is wired, UVW, red, white, black, and so that helps with the phasing, wire it as instructed. So we'll take a quick peek at the motor here. So we've got the FHA with the E250. Okay, so that tells us how many counts per rev. And so we'll take a look at that with the HDM software. This is their private labeled setting up and tuning software. So we'll take a look at this. You can't use the CME2 software with this. It's gonna say, hey, proprietary encoder type. So on the basic setup, we've got brushless rotary. You see here we've selected Halls. You can phase correction, that's fine, but it's HD incremental E with Halls, right? There, it's in the data. So you select digital Halls. This is just what we do. Why we do it this way? Well, I don't know, because it's a Hall commutation and that's what we do. Maybe a CAN mode, whatever mode of operation, sinusoidal commutation, first it's the Halls for commutation and then it's incremental encoder. So we've got all the data for the motor here, 17C100 E250, 12 pole, 2500, 10,000 counts per rev, calculate initial tuning values. Yeah, okay. We can check the current loop bandwidth here. I got a fault I need to clear out. Clear fault. Okay, so yeah, let's start that. So 6,000 RPM, 100 revs per second, 12 poles, 6 electrical cycles, 600 hertz minimum. I got 800 hertz, that should be fine. Let's take a look at the manual phasing so we can enable some current. Give it 1/2 amp. Set the 0 position. Press forward. The black indicator moves. The motor goes negative. I inverted the feedback. Let's uninvert it. Go forward. Counts go up. That's good. The Hall's going backwards. See if we can get some UVW going here. So swapping some motor wires until I find it. Ooh, this is looking good here. There's a little lead there. Let's try 30 degrees. A little lead in the forward, little lead in the negative. I'd say that's pretty good. Okay, so we'll save that. Should be able to jog it here. I haven't tuned any of the loops yet, but just making sure it looks good. Good, now let's take a look at the loop tuning. Current loop, auto setup checkbox, gains. Let's give it a little bit more current. We'll do 1/2 amp. Looks pretty good. Could get a little bit more proportional out of it. Maybe that's a little too much. A little buzzy there. And let's get some integral out of it. Gets a steady state, no overshoot. That looks pretty good. Velocity parameters, go to the velocity loop, auto setup checkbox. If you have a big inertia, you might want to cut down the accel and decel. And I like channel 3, current actual. See what that looks like. So we're going to see where the gain doubles and then cut it in half. So you'll hear some buzzing when it gets too loud. I can hear a little buzzing. Yeah, it's buzzing. All right, and it buzzed at 400, so let's give it 200 to cut it in half. That'll give me some gain margin there. So the next trace should show me. Yeah, it still looks a little ringy, but we'll gain a little phase margin here by making it a single pole, 200 hertz. We can move it out a little bit. It gets a little less buzzy, but let's bring the gain down. I don't want too much. I don't have a load hooked up yet, but with no load, this looks pretty good. If you had too much integral here, you'd see some integral wind up, but it would get to steady state. So if you have a big inertia, maybe 100 hertz. If you have small inertia, maybe you could do 300 hertz. So there's a little integral wind up there. I'd say that's a little too much integral, so we'll knock it down in half, but we'll come back to it during position loop. So 10,000 is a single rev. There's 10 revs, and we'll look at, that looks like a pretty good trajectory. I got a limit here on the V loop. I don't want to go, well, this has to be bigger than the fastest speed I can command. So if I want to do 4,800, let's say 6,000 is the theoretical on that. Don't calculate again. And then you can set the V limit, maybe 5,000 is about the top speed that they're talking. Yeah, so you got voltage limited, so be careful. But you can set a limit 10 or 20% higher than what you want to do. So let's try a nice short little move here. Actual current, auto setup, channel 3, current actual. Okay. 10,000 plus another 0 should be 10 revs. That's a good little move. And we'll take a look at the gains. There you go. So yeah, the integral wound me up. I got a little overshoot there. So I can make this come in a little better. Should land a little flatter. the error is near 0 while it's moving. So we can, that's the feed forward term there. If you have no feed forward term, you get error while you're moving, but it tends to land in a little better. So this would be if you don't have any, you don't care about while you're moving, just endpoints. Just keep the following error down. This would be about, yeah, close to 1,000. That's a little ringy for EP, but we'll turn it down a little bit here. If you had a big inertia, you might see it bounce, but I'm going to turn the integral back on. I mean, the feed forward, 16.384 is 100% forward. Be small error while I'm moving, and then it'll settle, but this is settling with a little bit of, let's try, I got a little more PP term there, so let's see if we can get the integral to overcompensate a little bit. Then we, yeah, there it goes, overcompensate. Let's see, 5. See if we can get it to come in for a nice 0 landing. There you go, plus or minus a count. I like it. So that's all good. Don't forget to save the flash. Maybe save to a disk. You can save a CCX file. You know, call it whatever you want. Scope traces you can save to disk too if you get a nice image to look at. And it looks good. I think we're done for today. Just like the cup says, this is good. Thanks for watching.